Hi class, welcome to today's lesson. Today's lesson is going to be lesson 2, graphing exponential equations. Your homework is listed here at the top as always. I actually went and highlighted the questions you should do in your worksheet as well, but it's going to be questions 390, or pages 390 to 393. They're the ones that are just posted. Lessons numbers 1 to 2, 4, 7 to 9, and 12. So by the end of the lesson, you're going to know the following. You're going to know the difference between the graphs, equations, first and consecutive ratios of linear, quadratic, this should actually says first, second, and consecutive ratios of linear, quadratic, and exponential equations. Basically, you'll know that for a linear equation, the first differences are the same. For a quadratic equation, the second differences are the same. And something new today we're going to be learning is consecutive ratios. Those are the same for exponential relationships. You'll know how to compare different bases and their impact on the different shapes of exponential relations. You're going to know how to graph exponential relations. And then you'll be able to compare first, second, and constant ratios to determine what type of relation a function is, as well as read and decipher different pieces of information from the graph form of an exponential relation. So let's start off with our first one, a little bit of an introduction to the difference between the three. So we know linear relationships have the y equals mx plus b. This is the stuff you learned in grade 9. If you go back to it and you think about it, linear equations are just a straight line on the graph, right? So I'm just going to go in here and I'm going to change this one to a green marker. Right, so you have just a straight line on the graph. So if I go here to a graph, a linear relationship is going to look something like this. Right, just a straight line through the graph. That's what it's going to look like. If you have a quadratic relationship, the first or second differences, in a linear relationship, the first differences are equal. The ratio of consecutive y values, which we'll be talking about, are not equal. Then we move on and we learned about quadratic equations, which the graph of them look like a parabola or a U-shaped curve. So they look something like this. And I'm just going to go draw it in. Right, so our parabola looks something like that. I'm just going to go highlight this here in pink. Right, the equation of the line was either y equals ax squared plus bx, or in vertex form it used to be y equals a bracket x minus h squared plus k, right? And in this situation, the highest degree of this function is 2, right? The highest x has a 2 on it, and this one it's 1. With quadratic relationships, the second differences are equal and the consecutive y ratios are not. Last but not least, this is the one that we're going to be learning about today, and we call them exponential functions, right? The graph of these looks kind of like it's like almost a straight line at one end, very, very small increase, and then there's a rapid increase on the other hand. It's kind of like a half of a parabola with the tail. Right, and the exponent is x, right? So it looks something like y equals bx, and b is a positive constant, right? And it's not equal to 1. And we'll talk about how those work today. In this situation, the first and second differences are not equal, and you'll have something that we call a ratio of consecutive y values. So we'll talk about how that works. Okay, so just so you know what this kind of looks like, it looks kind of like this is what a exponential function will look like. So I'm just going to go label these. So this is an exponential, right? This is a quadratic. So these all are different types of graphs. Quadratic, and then your green one here. Your green one here is a linear function. Okay. So moving forward, we're just going to go in and use Desmos to show how the graph changes when you're using the following graphs on Desmos. So if you could go in and just draw these graphs for yourself, I'm going to draw just a couple. So I'm going to draw 2x and 5x, and we're going to compare 0.1x and 0.4x, and then 1 to the power of x. Okay, so those are the ones we're going to compare in this class, but I actually want you to give it a shot. Try comparing all of them, But for the purposes of time, right, I'm just going to go through and do a few with you because those few will give you an idea of what we're kind of working with. So 0.1. And I'm just going to pull up Desmos and we're going to get started from there. And I'm going to do 1x because one of the things is that it can't be, b can't be positive 1. B cannot equal 1. Therefore, we would not graph this in real life. Okay, so let's just go here and pull up our Google Chrome. We're going to go to Desmos, graphing calculator, right? And we're just going to type in our different functions. So let's start off with y is equal to 2 to the power of x. So if you go and you type in 2 to the power of x, that's what you'll get, right? And then if you, oops, sorry, I'm just going to leave the x up there. Then the next one is y equals 5 to the power of x. And let's just go in and compare these two. So notice how with the 2 to the power of x, it's kind of more of a slow increase of the curve, right? Whereas with the 5, it's kind of a steeper of an increase. That's an important thing to take note of there. As the number, like the base value goes up, that big base of your exponent goes up, the steepness of the curve is faster, right? Steeper. Sorry, just gotta put that back in. Oops. And then we're going to go on and try doing y equals 0.1x, 0.1 to the power of x. Notice how here, these ones are kind of going, you know, you start over here and then you go up like this. This one, you kind of start up high and you come down, right? So instead of going up like this, you're kind of coming down on this side. Right? So that's what happens when you have a fraction there instead. Instead of your exponent getting larger or your number getting larger, it's actually getting smaller and smaller, your value. Let's do y is equal to 0.4, 0.4 to the power of x. And the same thing, the decline over here, oops. The decline over here seems to be a little slower. Right? So when your fraction gets smaller, your decline is slower versus when your fraction is bigger, your decline is faster. Just like when your number is larger, your incline is faster versus when your number is smaller, your integer is smaller, your incline is slower. Okay? So a few things that we learned from this is that when you have a 0.4 or a decimal or anything that's under 1, really, what you're basically going to be doing is you're going to be having a graph that is declining, right? So it's kind of a decline. And then if you have a whole number like an integer, it's increasing. So it's rapidly increasing. The other thing you need to notice is that if your base for an incline is larger, right, then you'll have a larger incline. If your fraction is smaller, right, so 0.4 versus 0.1, 0.4 is less than 0.1, you'll notice that it's smaller. The incline is smaller, okay? And then the last one we wanted to do was, I'm just going to click enter here, was the reason that we can't have y is equal to, y is equal to 1 to the power of x, to the power of x, is because it's just a straight line. It's just a straight line because 1 to the power of any number, 1 times 1 times 1 times 1 times 1 is always going to be 1. So it's just a straight line. Okay? Just a straight line. Okay? So exponential forms are relations that are in the form y equals b to the power of x, where b is greater than 0. So b cannot be negative, and b cannot be 1. Sorry, cannot be a negative number or 1. Because b to the power 1 to the power x is always just going to be 1. So it'll just be a straight line. Okay? So if your b value is more than 1, so it's a positive number, positive whole number, right? So I'm going to write that in. A positive whole number, right? On the left side of the graph, it's going to begin super low, close to the x-axis. It'll never touch it. So even if you notice here, right, if you zoom in and you look at any of these, they never touch x. They just get really, and some of them closer than others, they just get really, really close, but it's never actually 0. So if you notice, it never actually touches the x-intercept. It just gets super, super close to the point where it feels like it's touching it, but it's not. Right? So they're always, they get super close, but they never actually touch the x-intercept. Right? So there's no x-intercept. It just gets there, it barely touches it. That's something that we call an asymptote. Just a cool word to know. You don't really need to know it. Just called an asymptote. Right? And if you move from the right to the left, you'll notice that the graph increases slowly for x values, for negative x values, right? So it'll go all the way up, up, up as you go more to the x. Right? The graph passes through 1, right? So, or passes through 0, 1, which makes sense because anything to the power of 0 is 1, right? So it passes through 0, 1. The graph increases rapidly for positive x values on the right. So you'll notice that it starts to get larger for the negative values. See, it's going up slowly, right? But when it gets to the positive value, it starts going up super fast. Okay? So yeah. The larger the b value, the steeper the graph is on the right. So if it's 5, it's going to be better than 2. It's going to be steeper than 2. If it's 10, it's going to be steeper than 5. All right, so let's try to graph one of these by ourselves. And the first thing we're going to do is I'm going to teach you how to find the x, to find the y's. So you always use the same x's. You're going to use -3, -2, -1, 0, 1, 2, 3. Right, unless you can't use negative numbers because, I don't know, x is time or something rather. But we always like to use those basic points. So I know y is equal to 2 to the power of x. So now my x is the exponent. So I'm going to sub this x value in to this exponent. So it's -3. So if I put 2 to the -3 into my calculator, so actually let's pull up our Desmos calculator as well. Right, so I'm going to do 2 to the power of -3, and it's going to give me 0.125, or if you want to find the fraction, it's 1/8. So let's just go in here. I like to do 0.125 because I know I'm going to be graphing this eventually, and I don't like graphing fractions. I think it's just easier to graph decimals. So then I have y equals 2 to the -2. Again, that's going to give me 0.25, right, or 1/4, whichever way. 2 to the -1 is going to give me 0.5. Y equals 2 to the power 0 is always just going to be 1. And I'm just throwing these into my calculator. Y equals 2 to the 1, that's going to give me 2. Y is equal to 2 to the power 2 is going to give me 4. And I'm just putting in my x's. So in this situation, only my exponents are changing. The 2 stays the same at the bottom. The base stays the same. Okay? And that's that. So let's go find our first differences. Our first differences are always going to be y2 minus y1. Right? So let's do 0.25. minus 0.125, and that gave me 0.125. Let's do 0.5 minus 0.125. I'm just going to do it in the orange color. 0.5 minus 0.125 is going to give me 0.5, or 25, sorry. And again, I'm just throwing these into my calculator to do the math. 1 minus 0.5 is going to be 0.5. 2 minus 1 is going to be 1. 4 minus 2 is 2. And 8 minus 4 is 8. Minus 4 is 4. Notice how the first differences are not constant. This is not a linear relationship. But we knew that because a linear relationship has y equals mx plus b. I would go ahead and find the second differences, but right now you don't need to worry about that. Let's use our numbers from here and find the constant ratio. So instead of doing 0.25 minus 0.125, I'm actually going to do 0.25 divided by 0.125. So I'm just taking 0.25 and 0.125 and dividing them. And that gives me 2. Then I have 0.5 divided by 0.125, right? Just 0.5 divided by 0. Sorry, it should be 0.525 divided by 0.25, and that's going to give me 2, right? And then we're going to go to the next one, 1 divided by 0.5, also 2. 2 divided by 1, 2, and then 8, 2, right? I'm just going to keep going. 4 divided by 2 is going to give me 2, and then 8 divided by 4 is also 2. Notice how the constant ratios here are the same. They're all 2. That's how I know that this is an exponential function. The constant ratios are also the base. You'll notice that it's 2 all here, and you'll notice that the base of this function also 2. So just write that in for yourself. It's a good thing to remember and to know that you did it right. Constant ratio equals base. Okay? So then I'm just going to go in and let's plot these points on our graph, right? So the first couple ones are kind of hard to plot just because they are really, really close to 0. So I'm not super picky about them. But then the rest of them get easier to plot just because there's such a big difference between all of them. Okay, so let's do this. So we have -3 and then our y value is 0.125. So like I said, really hard to plot that one, but that's fine. We'll try our best. So -3, it's like super close to 0, but not really. And then we have -2, which goes up to 0.25. Again, that's more like 0.5. So maybe like here, 0.5. 0 goes up to 1. 1 goes up to 2. See, notice how there's a larger graph now here. It's easier to plot. 2 goes up to 4. And then 3 goes all the way up to 8, right? And so our graph looks something like this. So it goes up like that. Okay, so it starts off super close and it just kind of goes off into both directions. It almost plateaus on the other side. So it's kind of like half a parabola, just with a tail on the end, right? So that's our basic graph for the first one. Let's go on and try doing one where you have a b value between 0 and 1. This is basically just a fancier way of saying fraction. Fraction or decimal, so like 0 point something. So 0.4, 0.8, something like that. Anything in between 0 and 1. So on the left, the graph will begin at a high value, right? So here you'll notice that the graph begins at a low value and then increases suddenly, right? When you have a fraction, right, it begins at a high value and decreases suddenly. It kind of like drops off like a cliff, okay? As you move to the right, the graph will pass through 1, right? So 0, 1, therefore the x-intercept is 0, 1, right? The graph decreases more slowly for the positive x values. So it'll start off as like decreasing rapidly and then it'll just kind of like even off. So instead of going off like this and shooting up, it'll kind of drop all of a sudden and then even off. The graph approaches the x-axis on the right, but it doesn't touch it. Same thing. There's no x-intercept. That's an asymptote. The smaller the b value, the steeper the graph on the left, right? As b approaches 1, the graph gets flatter and flatter until at 1 is just fully flat. So let's try to do our equations for this one. Now we have 0.5 to the power of x. You can also write this as 1 over 2 to the power of x. I like to just always have them in the fraction form. I find it easier to do the math. So here we're going to do y equals 0.5 to the power of negative 3. Right, let's go into my calculator and put that in. So I'm going to clear this. I'm going to put it in a bracket, 0.5. Always put the 0.5 in brackets, and then you're going to say to the power of, and I started with negative 3. So in this situation, it is going to be 8, right? So I'm going to just go back into my table of values here, throw in, 8. Right, same thing I'm going to do for this one. I'm going to put the 0.5 in brackets, and this time I'm going to raise it to negative 2 because that's what my x is. So I'm going to go back in here. I'm just going to go and erase this one and change it to negative 2, and it's 4. That's often a good trick to keep on hand, just to erase it one at a time. 0.5 to the negative 1 is 2. And honestly, if you think about this from yesterday, we have 1 over 2 to the power of negative 1, right? The negative 1 goes to the on here. Then if you flip it, you're left with 2 over 1, right? So it makes sense that it's that way. Just in case you were wondering where we were getting those numbers from what we learned from our first lesson. But I'm more than happy with you just putting them into your calculator. But just showing you. 0, anything to the power of 0 is just 1. Y equals 0.5 to the power of 1. That's just going to be 0.5. 0.5 squared is going to be 0.25, right? And then y equals 0.5 squared. Cubed is just going to be 0.125. And again, these are just numbers I threw into my calculator. That's how I found them. Right? Then let's go in and find the first differences here, right? So 4 minus 8, right? Always the bottom one from the top one. Negative 4. 2 minus 4, right? Negative 2. 1 minus 2. Negative 1. And like honestly, in this situation, what I like to do is I actually like to do the first differences and constant ratios together because I find it easier to remember the numbers. So if I'm doing 4 minus 8, instead it's going to be 4 over 8, which is going to give me 0.5. 2 minus 4, so I'm going to do 2 over 4, which is going to give me 0.5, right? And then I'm going to do 1 minus 2, which is negative 1. 1 over 2, also 0.5. 0.5 minus 1, 0.5. And 0.5 divided by 1 is also 0.5. 0.25 minus 0.5 equals 0.25 or negative 0.25. So 0.25 divided by 0.5 is going to give me 0.5. And then we have 0.125 minus 0.25, which is going to be negative 0.5. This is also 0.5. Sorry, y'all. Negative 0. Sorry, this is 2.5. Losing it. Right? And then this one is negative. Sorry, I'm just going to write underneath. Negative 0.125. Whereas if you do 0.125 divided by 0.25, it's going to be 0.5. So notice how the first differences are not equal. So this isn't a linear equation, but the constant ratios are. And the constant ratios are 0.5, so you know that your base is going to be 0.5, which makes sense. And then it's an exponential equation. Okay? So let's go in and graph these points. So I like to just keep a copy of this on the side on my screen. You'll have a copy of it in front of you while you're doing your test. I'm just going to scroll down so that I can show you how I'm making the points better. So our first point is -3 and 8. So let's go to -3, -3, and then at 8 we're going to make a point. Then we have -2 and 4. So -2 and 4. Then we have -1 and 2, 0 and 1. Then +1 and 0.5. 2, and it kind of tapers off like this. So I'm just going to draw in the curve. So again, you'll notice it's kind of just tapering off, getting really close to 0 but not touching. So notice getting really close to 0 but not touching, almost leveling off at the end. And that's what my graph is going to look like. So that's what it'll look like for a fraction. This is what it will look like for a larger number. Okay? Or an integer. So let's do an example together and like how to read these. So it says York's population, P, is projected to grow until 2031 based on the relation 610,000, where n is the number of years after 1996. So we're starting off with 1996 when they started measuring the population, and we're measuring the number of years after that. So it says to sketch a graph of the relationship, which I already did. I just drew it in because the numbers were really large. So I just drew it in like that. And then it says to find what the p-intercept is, what it represents, what the projected population in the York region are in 2022 as well as 2031, right? But before we even get started on that, let's at least make our table of values. In the off chance that you have to sketch out a graph like this, I might just not tell you to sketch out the graph. I might just ask you to give me the table of values, just because the numbers are so large. I might ask you to sketch it out, but I'll go over how you could do that as well. I just didn't want to go in and have to draw all of this in. So let's do this. So at the number of years, n represents the number of years after 1996. 96, and P represents the population, so the number of people. Number of people. Okay, so let's go in and write down our information. So here, if the number of years after 96 is 0, it just means that this is 1996. So we have 610,000. Right, times 1.029. N is the number of years after 1996, and we know it's just 0. Right, so we're just going to do 1.029 to the power of 0 is just 1. So I'm left with 610,000 times 1, which is just 61000. Okay? Let's find out after 5 years. So 5 years after 1996 would have been 2001, right? So let's go put that in. So in 2001, our population is going to be 0.29 equals 6 to the power of 5, right? So it's just going to be, let's do our exponent first. So I'm just going to go pull that up. It's going to clear all 0. And make sure it's in brackets, obviously. 1.029 to the exponent 5 is going to be 1.15. So I'm just going to multiply this by 1.15. And then let's do the multiplication. Let's multiply that by the number 610 times 610 0, 0. And that's going to give us that number right there. You can just put this all in at one time. It'll still be the same thing. And because you can't really have half for 0.6 of a person, just round it to the nearest whole number. So you have 7, 0, 7, 0, 3, 7, 3, 10. 7, 0, 3, 7, 3, 10. And we'll just leave it at that. Okay. So I like to just honestly do this. I do 600,010 or whatever it was to the power of 10. So I just go into my calculator and throw it in all at once. So I do, let's clear all. 6, 1, 0, 0, 0, 0. Right? Make sure I have enough zeros. Point times 1.029 to the power of 10. Right, and when I plug all that in, I'll get my number right here. So it's 811,864.5. So I'm going to round that up to 0.5. So it's going to be 811. $811,865. Right, same thing I'm going to do here. 1.029 to the power of 15. I'm going to go plug that all into my calculator. So I'm just using my calculator beside me instead of using the on-screen one because I just personally find it easier to work with. And I get 936,614. Then I'm going to do the same thing here. 61000.1029 to the power of 20. Right, and I'm going to get 1080,531. So that's 1,080,531. 610,000. Just make sure you have all the right zeros in because then this gets messy. 25, and you'll be with. I'm just going in and filling out my chart basically with each number that I need to do. And obviously, like, you don't need to always show all your steps when you're filling out the chart, but show your steps otherwise, because sometimes if you make a mistake, I can't tell where you made the mistake, so then you just lose all the marks, and that's not worth it. So the more work you show me, the better it is. Okay, so those are all my numbers, right? So those are all my points. So I'm just going to go in and show you how I kind of graphed them in. So I went here and I said, okay, 5 is going to be at like 7 something. So it was like here. Right, 10 was at 800,011. So 10 was like here, and then 20 here, 25 was here, 30 was here, right? And we just plugged them in and joined them together. So you'll notice that it's, and 15, sorry, I forgot to add 15, 9 something, so it'll be here. Right, 35 was up here. So I just kind of joined together in that line. So it says, what is a p-intercept and what does it represent? So when does this pass through here? The p-intercept is right here. The point at which is 0, right? And we know that our p-intercept is when our n is equal to 0. So 0 years after 1996 have passed. Therefore, population during 1996. That's what it represents. The population in 1996. Let's go and find out what that is. So let's just go plug in 0 for n. P is equal to 610,000 1.029 to the power of 0. We know that's going to be 610, 0. Anything to the power of 0 is just 1. And if you go back and you look, you can actually find the point where n is equal to 0. We already found that value, and it was just 6/1000. So therefore, that means in 1996, the population of York Region was 610,000. And that is what I want you to be able to take away from this. I don't care if you know how to graph it. I care more do you know how to read a graph, because these graphs are actually really important. We use exponential modeling for so much stuff. So knowing how to read them is super important, especially with COVID. COVID is an exponential function, so we'll talk about how to read that as well. Many viruses, many compound interest formulas. All of this stuff is exponential. Which is why if you invest $100 today, right, you'll have way more than if you just got $100 every week in your bank account, because it grows exponentially. Same with debt. Debt also grows exponentially. So we'll talk about that when we talk about our finance unit. It actually leads us into it great. So then, what's the projected population of York Region in 2022, right? So the first thing you want to find out when you're looking for what is a future value, right, is, okay, what is n in 2022? Because if we're looking for population, what is n in 2022? We can find that out because n is a number of years after 1996. So I can just do 2022 minus 1996. It's kind of like finding your age. If you wanted to know how old you were today, or how old you would be in 1990, or how old you would be in 2022, you take the year and you subtract the year you were born. So let's do 2022 minus 1996. That should give us 26. So we're looking for how many years after 96? We're looking for 26 years after 96. Right? So let's go plug in n equals 26. So P equals the population equals 610,000. 1.029, which is just our equation here, and to the power of n. And we know that n we can just substitute in in our n value of 26, right? And let's just do the math. So I'm just going to put this in our calculator. I already have it here. And instead of 10, it's going to be 26. And the population is going to be this number. It's going to be 1,200,082,713 people. 0.244, and you can't have 0.244 of a person, so you just round it to the whole number. So it's going to be, and I like to put commas in between numbers when they're this big. It's just good form. People. So therefore, the population in 2022 will be 1,282,713 people. Okay, and then naturally you want to highlight your statement. So by using that same logic, pause the video here and try to find out what it will be in 2031. Okay? So try finding out what it will be like in 2031. And we'll take it up together after you unpause. Okay? So hopefully you pause the video. So we're going to do the same thing. How many years after 96 is 2031, right? And the way to do this is to do 2031 minus 1996, and that's going to give us like 35, right? Therefore, our n value is going to be 35, and we're just going to go plug it into the equation. So we're going to say, okay, P equals 610,000,1.029 to the power of n, right? Just going to plug in this n value here. $26. And let's go plug that into our calculator. And luckily I already had, it shouldn't be 26, it should be 35. 26 was the last one. 35. Let's go plug in 35 instead of the 26. 35. And that's going to be 1,659,82.3. So we'll round it up. So we know the population is going to be 1,659,082 people. And naturally we want to write a statement. Therefore, the population in 2031 is expected or projected or will be and that is the answer. And that's it. So again, if you go up here and you go into our homework pages, page 390, 1 to 2, 4, 7, 9, and 12, you're going to have some word problems and you're going to have some straight just answer problems where you're graphing and you're determining the equation. Really good practice problems. Go through it. Next lesson, we'll actually be doing a little bit more word problems, talking about half-life and exponential decay. Okay?